Hello students, welcome to Pi Academy, the place for mathematics and science. Dear students, in the last class we were discussing the chapter real numbers. Now let's go for continuing this, and today is 8th period of this chapter. Dear students, you must remember that we have been learning about this chapter in detail by solving plenty of problems. And in yesterday's class, we solved many statement problems on HCF and LCM by using fundamental theorem of arithmetic. Do you remember what is the next concept we had discussed? Yes, you are right. This is revisiting irrational numbers. Then recall the definition of irrational numbers with me. There are two definitions. First one, a number which cannot be expressed in the form of P by Q, where P and Q are integers and Q is not equal to 0. Then what is the second definition? Yes, recall with me. A number whose decimal expansion is non-terminating, non-recurring. Right? And we started proving the numbers like root 2, root 3, root 5, root 6 and so on as irrational numbers. There are two methods. What are those? Yes, first one is division method and second one is contradictory method. Division method already you had learnt in 8th standard. I hope that you have remembered. And second one, contradictory method, from which we are going to prove some numbers as irrationals in this academic year. What is contradictory method? Yes, the method in which our assumption is reverse of the given statement is called contradictory method. Yesterday we proved root 2 and root 3 as irrationals, right, by the same method, contradictory. Only for the sake of making you to recall the steps, I have taken one more example. Observe that it is, prove that root 5 is an irrational number by contradictory method. Yes, let's go for proving it by contradictory method. Then what should be our assumption? Yes, let root 5 be a rational number. If it is a rational number, how it should be written? Yeah, it can be written as, that is root 5 is equal to P by Q. Then what are P and Q? P and Q are co-primes, and another important thing is Q is not equal to 0. We also know that if Q becomes 0, then this becomes undefined term in mathematics. Next, what is the next step? Yes, correct. Squaring on both the sides, then you will get root 5 whole square as 5, P by Q whole square as P square by Q square. Then solve Q square and by cross multiply. Q square equal to P square by 5. Now you tell, what is the meaning of RHS? It means 5 divides P square. If 5 divides P square, then 5 also divides what? Divides P. Reason according to theorem 1.3. Then what is the meaning of 5 divides P? We can write that 5 is a factor of P. Now you may call this as equation 1 and you can call this as statement alpha. Just we have come to know 5 is a factor of P. Next, look here. I go for taking substitution for P. The reason is we have to show that P and Q are not co-primes. That's why let us say P is equal to 5k. Why it is 5k only? Because we are proving root 5 as irrational. Hence it is 5k. Then squaring on both the sides. P whole square is P square. 5k whole square is 25k square. You may call this as equation 2. Substitute equation 2 in 1. On substituting equation 2 in 1, then observe here equation 1, Q square is equal to P square by 5. What is P square? 25k square by 5. Now 5 ones are 5 5s are 5k square. Q square is equal to 5k square. Then solve k square. K square is equal to Q square by 5. Then what is the meaning of this? Yes, 5 divides Q square. if 5 divides q square, can we write 5 also divide q? Yes, according to theorem 1.3. Then what is the meaning of 5 divides q? You can write 5 is a factor of q also. You may call this as beta. See, from alpha and beta, 5 is a factor of both p and q. But here what we have assumed, p and q, they have the factor only one common factor. But from alpha and beta, what you can go for concluding? Yes, you are right. From alpha and beta, we can say that p and q are not co-primes. Actually, our assumption was they are co-primes. Then at last we have got they are not co-primes. Then what do you say about our assumption? Whether it is right or wrong? Yes, you are right. It is. Our assumption is wrong. Therefore, our assumption is wrong. If our assumption is wrong, you can go for writing hence root 5 is an irrational. Just for the sake of making you to recall the steps, I took this example. Yes, I think you have already practiced the problems like this. These are very important in the examination point of view. Just go for copying from there to here. Yes, quickly. Now, we will move on to the second type of problem. Just observe that. Prove that 5 minus root 3. What? Can you guess what it is? Whether it is rational or irrational? Then, look here. What do you call 5? It is a rational number. Root 3 is an irrational number. Difference of rational and irrational is, so you have already learned that, is an irrational, right? So now you are going to prove that 5 minus root 3 is an irrational number. Again, by which method? Contradictory method. Here I'll write. By contradictory method, our assumption should be reverse of the given statement. What is that statement? Given statement is 5 minus root 3 is an irrational number. So our assumption, let 5 minus root 3 be a what? A rational number. Or just you can write rational. If it is rational, how can it be written? Yes, you are right. It can be written in the form of P by Q. Then what are P and Q? Correct. They are co-primes. Then, and what is about Q? It is not equal to 0. Will you go for squaring on both the sides? You can go for that. But that takes many steps. I go for teaching you in a simple method. The reason is, here already we have proved root 3 is an irrational. Hence I go for separating it. See that 5 is there. Then take P by Q to the left hand side. It becomes minus P by Q. Minus root 3 is there. Take that on the right hand side. It becomes plus root 3. Clear? So when you after solving root 3, it will be easier for squaring on both the sides. Let us go for squaring on both the sides. Or still if you want to simplify, you can. Look here Q, then here 5Q minus P. Q is LCM. 5Q minus P is equal to root 3. This can also be written as root 3 equal to 5Q minus P by Q. I go for teaching you this in a simple method. Observe. What do you call P and Q? They are co-primes. Then can you say that they are rationals? Yes, they are rational. What about 5? That is also rational. Here I'll write P, Q and 5 are rationals. If they are rationals, what is it about 5Q? Is a rational. 5Q minus P, a rational. Rational by rational is also a rational. Then can we say that whole phi q minus p by q is a rational, right? Yes. If this whole term is a rational, that is equal to what? Root 3. Root 3 is also a rational. Is a rational. But already we have proved root 3 what? Root 3 is irrational. So we know that root 3 is an irrational. Irrational. Clear? Then what about our assumption? Our assumption is wrong. Therefore, our assumption is wrong. Hence, 5 minus root 3 is an irrational number. Clear? Very important one. Can be given in the examination for 2 marks. Very simple. 5 minus root 3 by contradictory method, assume that as rational, and it is expressed in the form of p by q, where p and q are co-primes. Then you just go for solving root 3, then it will be easier. Transfer minus root 3 to the right hand side becomes plus root 3, and p by q to the left hand side, it becomes minus p by q. Take LCM, q, multiply LCM with both the terms, 5q minus p, that's equal to root 3. Then it can be written as root 3 is equal to 5q minus p by q. Because a is equal to b is nothing but b is equal to a. Now, here we know that p and q are co-primes or they are rational numbers, even 5 also. When all these are p, q and 5 are rationals, then this whole statement becomes rational. That is equal to root 3. That is also a rational, right? If root 3 is to be assumed as rational, but we have already proved that root 3 is an irrational number. Therefore, our assumption is wrong. Hence, 5 minus root 3 is an irrational. Okay? Yeah. Please pause the video and copy from there to here quickly. Yes. One more problem. Observe. Show that 3 root 2 is irrational. By the same method, by contradictory method. Contradictory. How do you go for writing? What should be our assumption? Let 3 into root 2 be a rational. If it is a rational, how do you write? 3 root 2 can be written as p by q, where p and q are co-primes and q is not equal to 0. P and q are rationals. Then here also we have an irrational number root 2, which it has already been proved. Hence go for solving root 2. Root 2 is equal to p by transpose 3 to the denominator of RHS. It will be 3q. Right? Now look here. Here p and q are rationals. What about 3? That is also rational. Here I'll write p, q and 3 are rationals. Now you tell that. 3 is a rational, q is a rational, 3q rational, p rational. Then p rational by rational, that is also a rational. Hence we can write p by 3q is a rational. If it is a rational, this whole term is equal to root 2. Root 2 is also a rational. But we all know that what? Root 2 is an irrational number. Irrational. Then what is about our assumption? Assumption is wrong. Therefore, our assumption is wrong. If it is wrong, then what you can say? Hence, 3 into root 2 is an irrational number. Clear? Such a simple proof. Okay. These are the problems which are given in NCERT textbook. They are all worked examples. Now we are moving to exercise problems. That is exercise 1.3. I'll write here. Please don't go for copying. Just keep observing the board. Exercise 1.3. In that, the very first question is, it is prove that root 5 is irrational. Already in the very beginning only we have proved that one. So we can write proved. Second question is there. The second question is prove that PT, that means prove that 3 plus 2 into root 5 is irrational. Same thing. Here we have binomials, right? Two terms are there. Let us go for proving this. By which method? By contradictory method. According to contradictory method, how do you go for writing? We are going to assume that let 3 plus 2 root 5 be a rational. If it is a rational, it should be in the form of P by Q. 3 plus 2 root 5 is equal to P by Q. What are P and Q? P and Q are co-primes, are rationals, and Q is not equal to 0. Then here, which one is proved as irrational? Yes, it is root 5. Then go for solving root 5. I'll write 2 root 5 as it is, which is equal to P by Q. Transfer 3 to the right hand side, minus 3. Then it is equal to, take LCM, Q. Multiply LCM with both the terms. Q get cancelled, P will remain, minus. Multiply LCM with second term, it is 3Q. Understood? So 2 root 5 is equal to this much. We want only root 5. Here I write. Root 5 is equal to P minus 3Q whole divided by transposing 2 to the denominator of RHS. It becomes 2Q. Understood? Yes. Now, observe here, RHS part. What do you say about P and Q? They are rationals. 2 and 3, we know that they are also rationals. I can write P, Q, 2 and 3 are rationals. If they are rationals, now you say that. What do you call 3Q? Rational. 2Q? Rational. P minus 3Q? Rational. Rational by rational? Rational. Right? Hence we can write P minus 3Q by 2Q is a rational. And this is equal to what? Root 5. Root 5 is also a rational. But we all know that what? It is root 5 is an irrational number. Is it not? If it is irrational, what about our assumption? P, Q, 2 and 3. We have assumed them as rationals. So our assumption will become wrong. Therefore, our assumption is wrong, or our assumption contradicts the given statement. Assumption is wrong. Hence, 3 plus 2 root 5 is irrational. I hope that you have understood both of them. Both are important. Please go for copying from there to here. Pause the video, copy up to here quickly. Now let's move on to the third problem given in that exercise number 1.3. In that 3 sub questions are there. They are also related to proving irrationality of numbers. See that. Prove that the following are irrationals. In that first one, 1 by root 2 is there. Again, it should be proved by contradictory method. As it is contradictory method, we will write 1 by 2 as, so we have to assume, let 1 by root 2 be a rational. If it is a rational, how do you go for writing? 1 by root 2 is equal to P by Q, A by B, M by N, it is all left to you. P by Q. Then what are P and Q? P and Q are co-prime integers, or just you can write co-primes, and Q is not equal to 0. Just go for solving root 2. Cross multiply root 2 here. Then here Q on cross multiplying comes to the numerator, P comes to the denominator. Clear? So it is Q by P, Q by P is equal to root 2, or root 2 is equal to Q by P. Both are same only. Now what do you say about P and Q? They are integers, right? They are also, all integers are rationals. So Q is a rational, P is a rational, rational by rational, that is also a rational. Here I will write P and Q are rationals. If they are rationals, Q by P is a rational. Q by P it is equal to root 2 is a rational. But we have already proved in the very beginning, that is, you know that root 2 is irrational. If it is irrational, therefore our assumption is wrong. Hence, how do you go for writing? You can write 1 by root 2 is an irrational number. Or just you can write irrational. Clear? Now, let's move on to second one. Second one is 7 root 5. 7 into root 5. Here again, proof by contradictory method. You have to write in full words. Contradictory method. Let 7 root 5, 7 into root 5, not 7th root 5, 7 into root 5 be a rational. If it is a rational, then how do you go for writing? So 7 into root 5 is equal to P by Q or A by B. Here also, where P and Q are co-primes or rationals, and Q is not equal to 0. Then go for solving root 5. Root 5 is equal to P by transpose 7 to the denominator of RHS. It will be 7Q. Root 5 equal to P by 7Q. Then what do you call P and Q? They are rational. 7, that is also rational. Here I will go for writing P, Q and 7 are rationals. Then what do you say about 7Q is a rational. Then rational by rational, again rational. So P by 7Q is a rational. If it is a rational which is equal to root 5 is a rational. So we all know that root 5 is an irrational number. Therefore, our assumption is wrong, or our assumption contradicts the fact that 7 root 5 is rational. Hence, 7 root 5 is an irrational number. Clear? Next, we will move on to third one. Third one is also simple. Please don't go for copying. Afterwards, I will give you time for copying the whole statement. Third one is 6 plus root 2. It should be proved as irrational. By which method? It is by contradictory method. Prove by contradictory method. How do you write? Assume let 6 plus root 2 be a rational. If it is a rational, we can write 6 plus root 2 as p by q. Many times we have taken p by q. This time I am going to take a by b. A by b. Then what are a and b? They are co-primes. And b, that is denominator, is not equal to 0. Then here, which is irrational? Root 2, right? Go for solving it. Root 2 is equal to a by b as it is. Take plus 6 to the right hand side, it becomes minus 6. Take LCM, it is b. Multiply LCM with first term, b get cancelled, a. With second term, becomes 6b. Root 2 equal to a minus 6b by b. Now here, a, b and 6, what are these? They are all integers, nothing but rationals. They are rationals. Then if they are rationals, what do you call 6 into b? Rational. A rational. A minus 6b rational. B rational. Rational by rational. Again rational. So we can write a minus 6b by b is a rational. And this rational is equal to root 2. So root 2 is also a rational. But we all know that root 2 is irrational. Therefore, our assumption is wrong. Then hence, what you can write? 6 plus root 2 is an irrational number, or just you can write an irrational. Hope that you have understood. So all three are proved. Just go for copying by pausing the video. Copy from there to here. Quickly. Yes. Now just we are moving to only few simple and important additionals with respect to exercise 1.3. Observe. Prove that root 2 plus root 3 is an irrational by contradictory method. Root 2 is irrational, root 3 is irrational. The sum of two irrationals is again irrationals, right? Now let's go for proving by again contradictory method. Let us assume root 2 plus root 3 be a rational number. If it is a rational number, it can be written in the form of p by q, no doubt. So root 2 plus root 3 equal to p by q. To make our calculation simple, I just go for assuming that rational as a. You may take b, m, n, whatever the letter you want. So then root 2 plus root 3 is equal to a. Here we have two irrationals, root 2 and root 3. Let us go for solving any one. I'll take root 2 as it is. Transfer root 3 to the right hand side. A minus root 3. Squaring on both the sides. I think you may be thinking that, sir, we could have done squaring on both the sides in the beginning without transferring, right? Let us see what happens. Root 2 plus root 3 equal to a. If squaring on both the sides, then it is root 2 plus root 3 whole square is equal to a square. It is of the form a plus b whole square. A square plus b square plus 2ab is equal to a square. Square and root get cancelled, square and root get cancelled. 2 plus 3, 5 plus 2 root 6 is equal to a square. Then 2 root 6 is equal to a square minus 5. Root 6 equal to a square minus 5 by 2. See that root 6, of course it is irrational. But root 6 can be expressed as the product of two irrationals having primes. that is root 2 into root 3. The product of two irrationals may be a rational. So that is why that will be more suitable than this. Clear? Even we can go for this also, but this will be more suitable method for proving. Hence I have solved root 2. Even you can go for solving root 3 also. Squaring on both the sides, then root 2 whole square is equal to a minus root 3 whole square. Then square and root get cancelled. 2 is equal to, it is a minus root 3 whole square. In which form it is? It is a minus b whole square. Expand this. A square minus 2ab plus b square. Right? I go for writing the same. A square minus 2ab plus b square. What is A? A only. Then b root 3. Here b root 3. It is equal to 2 is equal to a whole square, just a square, minus 2 into a, 2a into root 3 plus square and root get cancelled, 3 will be. Understood? Next, here we have root 3. We have already proved root 3 is an irrational. So just go for solving root 3. Hence, I take minus 2a root 3 to the left hand side. It becomes plus 2a into root 3 equal to a square plus 3. Take 2 to the right hand side. It is minus 2. Hope you have understood this. Then let me continue that here. Now 2a into root 3. Keep that in the left hand side as it is. It is equal to a square. What is 3 minus 2? It is 1 plus 1. Then let's go for solving root 3 only. Root 3 it is equal to a square plus 1 transposed to the denominator divided by 2a. Clear up? We all know that. What is a? A is a rational number. Then what about 1 and 2? They are also rational numbers. A square rational. A square plus 1 rational. 2a rational. Rational by rational, again rational. So here I'll write a, 1 and 2 are rationals. Then a square plus 1 by 2a is a rational. If it is, the whole term is rational, that's equal to root 3. Root 3 is also a rational. Then we know that, what do you know? Root 3 is irrational. Therefore, our assumption is wrong. Because when root 3 is irrational, it should also be equal to irrational. But here we have assumed this as rational. Yes. Therefore, our assumption is wrong. Hence, root 2 plus root 3 is an irrational. Clear up? Now you have to copy that. Just I give you two simple problems. You have to prove yourself. That first one is, so first one already it is over. Second one it is just a homework. Second one is you have to prove that root 2 minus root 3 is irrational. Third one, you should prove that root 13 plus root 17 is irrational. Clear up? And one more. Fourth one, 2 root 3 minus root 5 is irrational. So you have to, for practicing purpose, I have given these three problems as homework. Work out this. Now you have to pause the video and should copy it from there to here. Let's copy it. Dear students, just we finished about revisiting irrational numbers. right? Now we are moving to again visiting the rationals and their decimal expansions. Even we have already defined what is a rational. It can also be defined in two different ways. A number which can be expressed in the form of P by Q, where P and Q are integers and Q is not equal to 0, right? Second definition, a number whose decimal expansion is non-terminating, recurring or terminating. Clear? Terminating or non-terminating, recurring. See that particularly we are focusing on rationals and their decimal expansion. Just I told you that decimals with respect to rational can be expressed in two different ways. One is terminating decimal expansion and another one is non-terminating decimal expansion. Clear? Non-terminating recurring decimal expansion. Example, see that here 1.125, it is a terminating decimal expansion, and non-terminating recurring, okay, 0.3333 and so on. Non-terminating recurring, this can be written as 0.3 bar. Then what we are going to learn in this? We are going to learn an important concept, that is it possible to identify the given rational number has the terminating decimal expansion or non-terminating recurring decimal expansion without actual calculation. Now I go for taking some of the examples. See that example is 0.04 and another one is 0.125. Let me go for taking one more, 0.7. Then what type of decimal expansions are these? Yes, they are terminating decimal expansions, right? Okay. Now let us go for expressing them in the form of P by Q. How do you go for writing? 0.04 can be written as 4 by 100, because after decimal we have two digits. Then you can go for cancelling. 1s are 25s are, right? 4 1s are 4 2s are 8, 2 will remain, 24 5s are. 1 and 2, what are these? 1 and 25, these are co-primes, right? Because their HCF is 1. Then here 25 is a perfect square, it can be written as 5 square. Understood? Next, 0.125 is there. This can be written as 125 by 1000. Then this is equal to, it can also be cancelled. How? See that 125 1s are, 125 8s are directly. Then 1 by 8 is there. 8 can also be expressed as the exponent of 2 and 2q. Clear up? Next, 0.7. It is 7 by 10 and 10 can be written as 2 into 5. Understood? Now when you assume that x is a rational number, these are all these are rational numbers. How is their decimal expansion? It is, these are all terminating. And can they be expressed in the form of P by Q? Of course, P by Q. Then what are P and Q? They are co-primes, right? These are all co-primes. See that 1 and 25, 1 and 8 and 7 and 10. These are all co-primes. Observe their denominator. Denominator is nothing but Q. In which form they are? Either it may be in the form 5 raised to the power m, or it may be in the form 2 raised to the power m, or it may be having both. In general, I will write Q is equal to 2 raised to the power m into 5 raised to the power n. Then what are m and n? M and n are non-negative positive integers. Non-negative positive integers. Clear? It is all with respect to terminating decimal expansion. Next, if it is terminating decimal expansion, if the number has terminating decimal expansion, then its denominator, it will be in the form 2 raised to the power m into 5 raised to the power n. Now I am going to take the same example in the reverse order, like this. It is 1 by 25. The number is already in the form of p by q. Then again 1 by 8, p by q form. Then 7 by 10. All these are in p by q form. These are the rationals in the form of p by q, where p and q are what? They are all co-primes. Clear? Then let us go for writing their decimal expansion. 1 by 25 can be written as 1 by 5 square. 1 by 8 can be written as 1 by 2 cube. 7 by 10 can be written as 7 by 2 into 5. Then we have to express them in decimal form. How do you go for? Will you go for actual division? You may go for, or else another method is there. 1 by 5 square is there. Multiply 2 square to the denominator as well as numerator. It is equal to 2 square is 4. 4 ones are 4. Here 5 square into 2 square is there. Then I can write 5 2s are 10. 10 square. 10 square is nothing but 100. It is equal to 0.04. See that? Its decimal expansion terminates. Or else even you can go for finding the decimal expansion directly, as it's equal to, when you go for dividing 1 by 25, 0, 0, then 0, 100, 4s are 100. Clear? 0.04. Or this is 1 by 8 is there. 1 by 8, 0 point. Here put decimal and take 0. 8 ones are 8, 2 will remain. Take 0, 8 2s are 16, 4 will remain 40, 5s are 40, 0. It is 0.125. Then here 7 by 10 is there. You can write it directly as 0.7. See that the number is in the form of p by q, and the p and q are co-primes. If the q is in the form of 2 raised to the power m into 5 raised to the power n, then the decimal expansion of that number terminates. Clear? Very simple. If the given number has terminating decimal expansion, it can be expressed in the form of p by q, and q will be in this form. If the number is in the form of p by q and q is in the form of 2 raised to the power m into 5 raised to the power n, then the decimal expansion of that number terminates. Clear? And one more statement is there. This is also very simple. I go for taking this. You are very familiar with this. 22 by 7. What is its value? 3.142857, 142857, 142857, and it continues. So it is non-terminating recurring decimal expansion. Next, I write 1 by 3. It can be written as 0.3333 and so on. Non-terminating recurring. Next, if you go for taking 1 by 11, it will be 0.090909 and so on. All these are examples for number which are in the form of p by q, but their decimal expansion is non-terminating recurring. Observe their q. They are all in the form of p by q. Then q, is it in the form of 2 raised to the power m into 5 raised to the power n? No. 7, 3, 11 is there. Hence, we can say that it is non-terminating decimal expansion. Very simple conclusion. In p by q is a rational number. In p by q, if q is of the form 2 raised to the power m into 5 raised to the power n, then it is terminating. It has terminating decimal expansion. In p by q, if q is not of the form 2 raised to the power m only or 5 raised to the power n only or 2 raised to the power m into 5 raised to the power n, then it is non-terminating recurring. Clear? So I have taken all these examples because in your NCERT textbook they have given the statements with respect to these. Clear? Just I am going to give you the simple points like that. The decimal number is terminating. It can be written in the form of p by q. Then q will be in the form of 2 raised to the power m into 5 raised to the power n. Now the number will be there, p by q. In that p by q, if q is of the form 2 raised to the power m into 5 raised to the power n, then the decimal expansion of that number terminates. Here, third one. In p by q, if the denominator is not in the form of 2 raised to the power m into 5 raised to the power n, then it is non-terminating recurring. Clear? So now I go for writing the statements. Don't go for copying this. After writing the statements with respect to these three, you have to copy that one. Okay? Once I tell you that, just observe. Let x be a number, rational number whose decimal expansion terminates. So it can be expressed in the form of p by q, where p and q are co-primes and q will be of the form 2 raised to the power m into 5 raised to the power n. That means prime factorization of q will be in this form, where m and n are non-negative integers. Clear? Next, second one. A number, I am going to assume this as x, is a rational number which is in the form of p by q, where p and q are co-primes and q is of the form 2 raised to the power m into 5 raised to the power n. Then the decimal expansion of that terminates. Third one. Let us assume x is a rational number whose decimal expansion is non-terminating recurring if and only if the prime factorization of denominator is not of the form 2 raised to the power m into 5 raised to the power n. Okay? Yes. Now I'll go for writing all the statements. Dear students, observe here. Whatever I explained earlier, all are written in simplest way, like this. That is, in any rational number which is in the form of p by q, if q is of the form 2 raised to the power m into 5 raised to the power n, then its decimal expansion will be terminating. Right? In that p by q form, if the number has terminating decimal expansion, then q will be in the form 2 raised to the power m into 5 raised to the power n. Next, another one. In p by q, if q is not of the form 2 raised to the power m into 5 raised to the power n, then it has non-terminating recurring decimal expansion. Non-terminating recurring decimal expansion. Clear? Yes. Let's go through the statement. Look here. First one. Let x be a rational number whose decimal expansion terminates. I have already told you, if it is a terminating decimal expansion, it can be written in the form of p by q and q will be in the form of 2 raised to the power m into 5 raised to the power n. The same thing has been written. Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form of p by q, where p and q are co-primes, and prime factorization of q is of the form 2 raised to the power m into 5 raised to the power n, where m and n are non-negative integers. Clear? Next, here I have taken examples with respect to this. See, these are all terminating decimals. they are all written in the form of P by Q, where P and Q are co-primes, and the denominators of those can be written in the form of either 2 raised to the power m or 5 raised to the power n or 2 raised to the power m into 5 raised to the power n. Clear? Okay. Second one. The number is already in the form of P by Q. In that P by Q, if Q is of the form 2 raised to the power m into 5 raised to the power n, it has terminating decimal expansion. Look here. Let x equal to P by Q be a rational number such that the prime factorization of that Q is in this form. Then x has a decimal expansion which terminates. I have written the same. These are the numbers which are already in the form of P by Q, where P and Q are co-primes. Then the denominator, observe that denominators, they are in the form of 2 raised to the power m into 5 raised to the power n. Hence, their decimal expansion will be terminating. Next, third one. A number will be in the form of P by Q, but Q is not of the form 2 raised to the power m into 5 raised to the power n. Under such condition, its decimal expansion will be non-terminating recurring. That is only the statement. That x equal to P by Q be a rational such that the prime factorization of Q is not of the form 2 raised to the power m into 5 raised to the power n, where m and n are non-negative integers, then x has a decimal expansion which is non-terminating recurring. These are the examples. P by Q form, but denominator observe 7, 3 and 15. 7, just it is not of the form in this form. 3 is not in this form. When you go for taking 15, say 15 can be written as 3 5s are. 5 is there, but there is no, but there is 3 also. 3 should not be there. Either there must be only 2 or only 5 or both 2 and 5. As 5 is there, hence we can say that it is not of this form. Therefore, their decimal expansion will be non-terminating recurring. Clear? Now, you should go for copying from here to here. With these 2 points are very important. In addition with that, this theorem, example. Next theorem, example. Next theorem, example. Copy it. Okay. Dear students, now let us begin the exercise 1.4 with respect to just what we learned regarding decimals. Observe, the first question is like this. Without actually performing the long division, state whether the following rational numbers will have terminating or non-terminating recurring decimal expansions. Non-terminating recurring decimal expansions. They are given the numbers. First one is 13 by 3125. Second one 17 by 8. Third one up to we have written fifth one. Now just focus on only first one. 13 by 3125. Please do remember in the rational number P by Q, if Q is of the form 2 raised to the power m into 5 raised to the power n, it has terminating decimal expansion. If it is not in this form, then we can say that non-terminating recurring. Clear? Observe that which is the denominator? Denominator is 3125. You have to check whether in this form or not. I go for writing 3125, finding the factorization of 3125. It can divisible by 5. 5 6 are 30, 1 will remain 12, 5 2s are 10, 2 will remain 25, 5 5s are. Then again 1s are 2s are 5s are 5, then 2s are 5s are 5 5 are. Yes, it is 13 by 3125. In this 3125, it is equal to 5 raised to the power 1 2 3 4 5. 5 raised to the power 5. This can also be written as 2 raised to the power 0 into 5 raised to the power 5. It has only 2 and 5. Therefore, what type of decimal expansion? Yes, it has terminating decimal expansion. It is of the form 2 raised to the power m into 5 raised to the power n. Therefore, it has terminating decimal expansion. Observe. I'll go for taking another one. Second one has been written here 17 by 8. 17 by 8. Very important. First you have to check that in that P by Q form whether P and Q are co-primes or not. If it is to be possible to simplify, you can go for that. But here they are co-primes. Now in 17 by 8, what is 8? 8 can be written as 2 cube. If you do not know, you can go for writing like this. 2 4s are 2 2s are. 8 equal to 2 cube. Can also be written as 2 cube into 5 raised to the power 0. Because 5 raised to the power 0 is 1. 1 into 2 cube is again 8. This is of the form 2 raised to the power m into 5 raised to the power n. Therefore, what do you say? The decimal expansion. It has terminating decimal expansion. You should write in the words. Clear? Next, I go for third one. What is third one? 64 by 455. 64 by 455. Observe these numbers. Are these co-primes? They are not divisible by any number except one. Yes, they are co-primes. I go for taking 64 by 455 as it is. Then go for finding the prime factorization of denominator 455. Then 5 9s are 1s are. Then 13 7s are. Look here. 455 is equal to 5 into 13 into 7. Is it of the form 2 raised to the power m into 5 raised to the power n? No. Why? See that the Q has 5, but along with that 13 and also 7 are there. But according to the condition, there must be only 2 or only 5 or both 2 and 5. So it is not of the form 2 raised to the power m into 5 raised to the power n, or the prime factorization of 455 contains 13 and 7. Therefore it has non-terminating recurring decimal expansion. Non-terminating recurring. It should also be written in words. Next, I go for taking one more, fourth one. It is 15 by 1600. 15 by 1600. Observe. Are they co-primes? No. They can be simplified. How? As they are divisible by, or as they end with 5 and 0, they are divisible by 5. I'll go for that. 15 by 1600 is equal to 5 3s are 15, 5 3s are 15, 1 will remain 10, 5 2s are 10, 0 will remain. 3 by 320. Now, in 3 by 320, what is the prime factorization of 320? Start dividing it by 2. 2, 1s are 6 are 0s are. 2, 8s are 0s are. 2, 4s are 0s are. 2, 2s are 0s are. 2, 10s are. 2, 5s are. It is equal to 2 how many times? 1, 2, 3, 4, 5, 6. 2 raised to the power 6 into 5 one time. Is it of the form 2 raised to the power m into 5 raised to the power n? Of course. Therefore, what type of decimal expansion it has? It has terminating decimal expansion. Hope that you have understood. Next, fifth one. It is 29 by 343. The given number is 29 by 343. What is in the denominator? 343. And what about its prime factorization? 343. It is divisible by which number? 2, 3. will not come, 5 will not come, 7 it comes, 7, 4s are 28, 6 will remain 63, 7 9s are, now 7 7s are 49, it is equal to 7 cube, it has no no 5, so it is not of the form 2 raised to the power m into 5 raised to the power n, therefore the given number, it has non-terminating recurring decimal expansion. Clear? See that without actual division you can just go for guessing whether the decimal expansion of the given number is terminating or non-terminating recurring. So hope that you all have understood. Now you just go for copying from here to here. Pause the video and write up to here. Now in this mail we have 5 more problems. I have written them here. Let's go for answering one by one. Now here 6th one. What is that? 23 by 2 raised to the power 3 into 5 raised to the power 2. It is very simple. You just observe in this number 23 by 2 cube into 5 square. What is in the denominator? Yes, 2 cube into 5 raised to the power 2. It is of the form 2 raised to the power m into 5 raised to the power n. Therefore, we can say that it has terminating decimal expansion. Very simple one. Even if you want to write that in sentence form. Now, I'll go for taking 7th one. 7th one is 129 by 2 square into 5 raised to the power 7 into 7 raised to the power 5. Look here. You can go for answering like this also. In the number, what is that number? 129 by 2 square into 5 raised to the power 7 into 7 raised to the power 5. What is in the denominator? Denominator is q. Q is equal to 2 raised to the power 2 into 5 raised to the power 7, 7 raised to the power 5. Is it exactly of the form 2 raised to the power m into 5 raised to the power n? No, 2 and 5 are there, but in addition with that, 7 is also there. You can write is, if you want to write in sentence, is not of the form. What is that? 2 raised to the power m into 5 raised to the power n only. Therefore, it has non-terminating recurring decimal expansion. Clear? Let me go for taking 8th one. 8th one is 6 by 50. Then will you go for taking directly 6 by 15? Is it possible? No. Why? Because they are not co-primes. They can be cancelled. Here 6 by 15. Both the terms can be cancelled by 3. 3 2s are 3 5s are. In 2 by 5, what is in the denominator? It is 5 only. 5 can be written as 5 raised to the power 1 into 2 raised to the power 0. Because 5 can be written as 5 into 1. 5 is written as it is. 1 is nothing but anything raised to the power 0. I have written 2 raised to the power 0. Is of the form 2 raised to the power m into 5 raised to the power n. Again, I have been telling you, if you want to write that in sentence, you can go for is of the form. Therefore, it has, what is it? Terminating decimal expansion. Next, 9th one. Let me go for taking 9th one. It is 35 by 50. What do you say? Are they co-primes? Not at all, because both are the multiples of 5. You can go for cancelling them by 5. 35 by 50 can be written as 5 7s are 35, 5 10s are. See that 7 by 10 can be written as directly 0.7. 0.7, whether it is terminating or non-terminating? Terminating. So here I will write the cube, that is 10, can be written as 2 into 5. This is of the form 2 raised to the power n m into 5 raised to the power n. Therefore, it has terminating decimal expansion. Now, let me go for taking the last one. It is 77 by 210. 77 by 210. Are they co-primes? Not at all. How do you say that? Yes, because both are the multiples of 7. Both can be cancelled by 7. How? Let me show that. 7 ones are 7 ones are. Here 7 threes are 0s. Now see that 11 and 30 are co-prime. Now in alright, q is equal to, what is in the denominator? 30. What is its prime factorization? You can go for finding. 30, 2 15s are, then 3 5s are. So 2 into 3 into 5. The prime factorization of q has 3 also. Therefore, it has non-terminating recurring, or else is not of the form. Exactly. 2 raised to the power m into 5 raised to the power n. Therefore, it has non-terminating recurring decimal expansion. Clear? So you can write in this way also. Next we have one more main, and we will go for solving that in the next class. And before concluding, dear students, let me tell you one thing. Whatever the irrationality of rational numbers have been proved, please practice them today itself, particularly root 2, root 3, root 5. Then again we took binomial like 2 plus root 3, and another type, it is root 2 plus root 3. Please practice them. They are all very important. Every year they are giving any one problem among those what I said now. Practice them as many times as possible. Next, after that, without actual calculation, we have decided if it is a rational number, whether it has terminating decimal expansion or non-terminating recurring decimal expansion. With the conditions, we have decided that you have to practice those also. Okay. With this, let us stop the class. Thank you.